Good day, everyone. Today we will demonstrate about the STM calculator, the strut method software that is inclusive in the RKALC software package. One of the very nice programs we've got is the coupling beam. Now, some people would like to design beams just using the normal beam theory, but if the stand to depth ratio is less than, let's say, 2 or 1 or even 3, Australia standard and international standards recommend using just-in-time method. Now, going to a heavily loaded header beam or a coupling beam in American terms, click on this one, and you see what we've got there on Mrs. Screen, the module that will allow you to show, to insert all of the parameters related to the header beam, their concrete F prime C, let's say 50 in this scenario. You got the thickness of the beam, depth of the beam, and the clear span between the walls, the wall piers on either side of the beam. Now, in this very case, the default example you got, the beam is lightly loaded, relatively at 2.12. It's not a big deal for beam reinforced with stirrups. But if you up the load to some 5 or 6 MPa, the challenge will be very big. Say 6 here. So you got 4, and this just reduce the beam thickness. So you got a 5 MPa. That is a very big shear stress on any beam. With the strut tire model that we've got, this one is taken from the famous paper introduced by Skidmore consultants when they were designing the Burj Dubai or Burj Khalifa. At that time, they had the limitations of ACI over maximum shear can be applied on the beam. And then they introduced this method, or this simplified strut-and-pine method or a moment for the beam. Now, we've translated this into the Australian standard, and you can, with this, guess the reinforcement that is needed for a beam like this, and then you will have the normal challenges that you see with safing this knot. For example, you've got the stresses are all more than the limits for CTT node. In this scenario, maybe we can think, oh, easy fix is going with the 65 MPa, but you still have a problem with the side stress. Then what is that? The side stress is basically the amount of tension you've got on this node. So it can be addressed by increasing the depth of the node, or let's say the depth of the structural reinforcement. The center of the reinforcement is here at 78 from the top of the beam. If we make it, for example, 100, so the beam depth or the node depth becomes at 200, essentially, as showing there, and all of the stresses are relaxed. You can go back to 50 MPa, and you see where we are standing. So the critical stress is at the side stress. So basically, increasing the depth of the node, we are getting closer. Let's say 120, very close, 125. So that is the beauty about this software. You can keep iterating without reconstructing the strut-and-tie model by hand, which is a very big problem. Now, you still got the basis stress, so the width of the node here can be increased to 120. So this beam now is all good to go. So, but you just need to be mindful that the beam reinforcement or the working reinforcement for this beam is passing through the center of the node. For example, you got the depth of the node is 125. So the total depth of your reinforcement layers will have to be 250 in order to pass by the center of the node. So your model will be all correct.